Hi, my name's Corey. I'm at the University of Oklahoma, and I usually like to start by talking. I was a general education teacher, and now I'm in a special education position, so sometimes I only get special education teachers who I work with mostly, but I was in the midst of getting put into a situation where over half the students in my class had a disability, and like another third of them, well, not that many, but maybe another fourth had a 504 plans. And all I had, have you all taken that one intro to SPED course all programs offer? And you're like, yeah, we got it, covered in this 1 3-credit course. And I floundered really bad. And that's what got me into special ed on the back end. So if any of you ever want to chat about any of that, I'd love to. My email's here at the bottom. At the very, oops, I didn't mean to do that. At the very end of the presentation, there's going to be a QR code up here along with a bit.ly, which is going to have this along with just a dumpster of resources if you teach math. And so, yeah, and you can always email me. So what we're going to try to start with, oh, and I don't know, did you all catch the dogs doing tug of war on this? I know it's hard to see. So what we're talking about today is this false war that's kind of been perpetuated, which is pitting conceptual knowledge versus procedural knowledge. And I want to make it really clear, I'm using the term conceptual knowledge and not conceptual understanding. And that's one of the kind of the big controversies is if you look at a lot of the cognitive psych literature, they talk about conceptual knowledge, and their definition of that oftentimes differs than when we hear people talking about conceptual understanding, such as the NCTM. So first, we'll talk about defining terms. We're then going to talk a little bit about the historical context and background to some of this, which will then pave the way to talking about what does research show about the relationship between conceptual knowledge and procedural knowledge within mathematics, and then we'll touch on what it might look, how that knowledge will dictate how we might think about providing math instruction. I might run the risk of getting too caught up in theory here. Okay, so I'm going to preface that here. For practical things, that's why I have a dumpster file. I have this dumpster folder with so much stuff. But I will take questions after too, if anyone wants to chat. So, defining terms. Have any of you ever seen this before? This roadmap to introducing vocabulary? Anyone? This is directly from Anita Archer's book on explicit instruction. And so the first thing we want to do with kids is we always introduce the word. And one of the things we want to do with students is when we introduce the word, we want it printed. When we, instead of just orally saying the word, we've seen from a couple research studies now, when students can actually see the word as well, they're going to retain it quicker. The other thing, my next session's on opportunities to respond. And so one of the things we can do is I would say, conceptual knowledge. Everyone whisper conceptual knowledge to yourself. Say it really loud. What did we just do for students? Anyone? What did they just now have? 2 opportunities to actually say the word. How easy was that? So now I will stop treating you like children, sorry. So our definition for conceptual knowledge is it's a knowledge of concepts which are oftentimes abstract or general principles in mathematics. That's what we're talking about when we're talking about what conceptual knowledge means in mathematics. And the other thing, and this is a really, really big point, because this is something I had a lot of misconceptions about previously. Conceptual knowledge can be implicit or explicit, which basically means students do not always have to verbalize that knowledge to show conceptual knowledge. And that's some of the ways where when you begin to think about how high stakes or standardized assessments, how do they oftentimes try to evaluate students' conceptual knowledge on math tests? They're making them write it down. And that's where, from an assessment standpoint, we begin to pick up a lot of construct irrelevant variance. And what that means is we are picking up students' writing knowledge, right? And perhaps language difficulty in trying to evaluate their conceptual knowledge. They might have that conceptual piece, they're having a hard time putting it into writing or reading. And then, so the 2 critical attributes here are it's focused on the knowledge of concepts which are abstract, and it can be implicit or explicit, depending on how we're trying to evaluate it. So here's one example. I might present the item 2 plus 9 to a student, and they use the join model of addition by starting at 9 and counting up 2. Did that student verbalize anything about their knowledge of the commutative property of addition? Did they explicitly say, I'm using the commutative? No, they didn't. Did they show conceptual knowledge by doing that? Yes, they did. So this would be a form of them implicitly demonstrating conceptual knowledge of the commutative property of addition. Is everyone cool with that one example? And I'm sure a lot of you can begin to think of a bunch of other ways students can do this. A non-example would be students using the partial sums algorithm to solve 2-digit by 2-digit addition problems requiring regrouping in the ones place value, right? That would actually be an example of, anyone want to guess? Procedural knowledge, okay? So what would be one example of a student demonstrating conceptual knowledge of the concept of equal groups from multiplication? So think about that for half a second. What would it look like for them to begin to show some form of conceptual knowledge for that problem? Everyone spend a second. If you want, I'm not the most friendly person, so I'm not going to make you talk to a stranger, but if you wanted to chat with someone sitting next to you, I'll give you 20 to 30 seconds to do that, okay? So 20 to 30 seconds, talk to a neighbor if you feel friendly. All right, anyone want to share out what they talked about? What would it look like for students to maybe demonstrate some form of conceptual knowledge for that? Yeah, go ahead.
We talked about like either 3 groups of 5, like 5 plus 5 plus 5.
Perfect. Yeah, so that group talked about them being able to read this as 3 groups of 5 and then representing repeated addition of 5 plus 5 plus 5 would be a form of them showing implicit knowledge of that. They didn't even have to verbalize it. Is everyone cool with that one example? And there's a bunch of other ways students could begin to show conceptual knowledge for that. I guess I do this all the time. I already answered this question at the beginning. But why do you think definitions for conceptual knowledge often will explicitly state that this knowledge doesn't need to be verbalized, right? And we just talked about this a second ago. When we begin to require verbalization, we might be picking up other variables that don't actually play into whether they understand the concept or not. So I'm sorry I did that. Okay, so the next one, anyone want to guess what our next term is? Procedural knowledge. Excellent. So everyone whisper procedural knowledge. Say it really loud. Say it in a funny voice. We just had 3 OTRs of saying procedural knowledge and it took all of 10 seconds. Okay, so procedural knowledge is the knowledge of procedures, which I probably should have reframed these because you're not supposed to use the word in the definition, I'm sorry. But with procedures, I do define procedures as steps or actions completed to accomplish a goal. And clearly, our critical attributes is it's a knowledge of a procedure, and the students need to be performing those actions seamlessly. Now, this is where there's been a lot of kind of controversy around, well, what is procedural knowledge? Because you can have, a lot of us, what's your first gut instinct when we think about procedures? Doing computation or algorithms, right? That's where our mind initially jumps to when we think about procedural knowledge. But you can have procedural knowledge in how to attack a word problem, right? I know I need to read the problem, I need to understand the problem, I need to schematically map that. That is showing procedural knowledge for a higher level task than just computation. And so we need to reframe on what we think about procedural knowledge. It doesn't always just have to be straight comp. So here's one example, and that's the one I used, right? Students using an algorithm to solve 2-digit by 2-digit multiplication, right? That would be demonstrating procedural knowledge if they're able to do that. A non-example might be a student evaluating triangles that are classified incorrectly. So a bunch of triangles, they're classified incorrectly. The student has to identify the errors and reclassify them as either isosceles, scalene, or equilateral. That would be conceptual knowledge. Okay, so a student is working on adding fractions that involve unlike denominators. Is everyone comfortable with that? How many of you teach 5th grade? That's what I taught. You spend all year on fractions. And it was terrible, and you're just beating your head against the wall. So what would procedural knowledge look like for that skill? So think about that for a second. What would it look like for a student to demonstrate procedural knowledge for that skill? Anyone want to chime in here? What would that look like? Perfect. So understanding that in order to add, I can't just add the denominators. So one of the steps in this procedure is make sure we're creating equal size groups through a denominator, and then they would go about adding the numerators, adding the denominators, and then simplifying. Okay, is everyone cool with that idea? Now, I had to really cut myself down because I could have talked about fluency for probably an hour. But in most definitions about procedural knowledge, it's not just knowledge. Oftentimes for procedural knowledge specifically, we talk about students being able to do it seamlessly. Sometimes we'll see the word automatic used. Sometimes we'll see the word fluency used. All right? So most definitions have this idea of, I ended up going with the word seamless rather than the others, but we'll talk about it in a second. How does this language of understanding seamlessness of doing it, how does that help us classify students along a continuum? So think about students you've worked with. What would it look like for one student who might follow the procedures versus another student who's following the procedures seamlessly? Anyone have examples of this in their practice? The difference here? I'll share an example. Is that okay? I was observing one of our undergrads last semester teaching, and she had an amazing task analysis, right? So students, step 1, step 2, step 3, step 4 to do this math. A bunch of the students were in there, had to keep looking at the task analysis, going back to the problem. Looking at the task analysis, going back to the problem. Is everyone following me? And the student was doing an amazing job, right? They were engaging in self-monitoring, self-evaluation, all of that was encompassed. That student was not seamless yet. Is everyone cool with that idea? Versus the other students, that the thing was still posted there, they didn't look at it one time, which would show seamless performance. And so that's kind of when we begin to think about what does it mean to actually show strong procedural knowledge. It's that not even having to think about it anymore. It becomes automatic. So here's my big warning. It is, at least to me, and so some people will argue a little bit differently, but it becomes very difficult to try to be like, this task is clearly just procedural knowledge, or this task is clearly conceptual. There's so much crossover between the two. So if we look at this one problem right here, 3 plus 4 plus 2 is the same as a number plus 5. Is everyone cool with this? What do most students put right here? Anyone want to take a gander? 9. Why do they put 9? Yeah, and they view the equal sign as a do something symbol. Does anyone know the next most common answer students write? 14. How would they get 14? They just add everything. Oh, I see numbers. I am adding because there's a lot of addition signs. So here's what I want to talk through now. We're working on this skill, right? This is a pivotal skill for students to begin to build pre-algebraic reasoning along with number combinations. What aspects of this skill would align to conceptual knowledge? What within here are students really having to pick up on that would fit under conceptual knowledge? Yeah, go ahead. Perfect. So one of the most pivotal aspects of this is understanding equality and our equal sign, and understanding that one side of our equation must remain balanced with the other side of our equation. Is everyone okay with that? I would say that's like probably the most pivotal for this. But what other aspects of conceptual knowledge would be present within this problem? Yeah, go ahead. Yeah, perfect. Understanding the concept of addition strongly, right? We have different models of addition, right? We have a part-whole model of addition where it's a set. We combine that set to create a total. We have a join model of addition where we're starting with a set and we're adding on to that set. And so having those really firm is going to be inherently important to understanding this problem. Now, within here, though, what would be procedural knowledge? Yeah, actually being able to do the strict math facts that are embedded here. Being able to quickly say 3, 4, and 2, I'm sorry, it's not 7, 9. And then, going back to the point made earlier, we have 9 on one side. What plus 5 yields 9, right? All of that would be inherently procedures. Okay, so historical context. Here's a couple quotes that I pulled about this. So you can see the one was written a while ago. So I'm sorry. And this was by Souter. It says, whether developing skills with symbols leads to conceptual understanding, or whether the presence of basic understanding should precede symbolic representation in skill practice is one of the biggest disagreements in math education. Okay? That was written a long time ago, right? And we're still having the conversation today. This one was even more to the point. A rush for procedural skill will actually do more harm than good. And then we can see this last one here. This is a self-plug. I have a Substacks, and I wrote an entire thing on NCTM's recent... has anyone seen NCTM's... they did a little white paper on procedural fluency. If you haven't read it, I recommend reading it, because in what I wrote, I highlighted a bunch of the good in there. But here's what they said. Conceptual understanding must precede, but then also coincide with instruction on procedures. And so it seems to be talking against one another. But there's a clear emphasis in some of these that we should be teaching concepts before procedures. Does everyone see that coming to the forefront here? And it's interesting because if we go back to Adding It Up, which was by the National Research Council back in 2001, it's a really long document. That link will take it to you. It's totally free. You can download a PDF version of it with an email. You can also just read it on the web for free. But they proposed this math rope. And in this math rope, we have these different kind of strands or ways of thinking about mathematics. So we have adaptive reasoning, strategic competence, conceptual. They use the word conceptual understanding, which I already talked about. I don't love that. They have productive disposition and then procedural fluency. And clearly what they said in the report is these 5 strands need to be interwoven together. So even way back in 2001, they were very clear from the beginning, we're not saying one is more important than the other or one should precede the other. They need to be worked on cohesively. Okay? So we need to do both. One thing, and this is a me thing, I don't love the math rope. Yeah, how many of you teach reading? We have Holly Lane right here if anyone wants to say hi afterwards. But Scarborough's rope, like we have these different models or ways of thinking about how reading develops. Math is just, our research is such in an infancy stage compared to reading. And so they had this rope, but I would argue really strongly they ignore declarative facts. So if you think about procedural fluency, right, we're thinking about doing procedures. How do I do a procedure? I need facts, right? And so there seems to be a disconnect of undermining how important declarative fact knowledge is in order to actually be able to demonstrate procedural fluency. And furthermore, building declarative fact knowledge is going to help with conceptual understanding. And here's the thing, we can talk about declarative facts such as what is 4 plus 5, right? We have all of our declarative facts for addition, subtraction, multiplication, division. But even declarative facts of, I know what that term is, right? So we saw if you have the word addend, right? Everyone familiar with addends, teaching little kids? A student being able to read addend and say, an addend is those two things, that is becoming a declarative fact for them, which is going to allow them to develop deeper conceptual knowledge of addition. So here's a problem. And I'm going to have you do a little bit of math, so don't hate me. But if you teach 5th grade, this is your wheelhouse. Here's a problem a student has to do. How many facts are in this problem? So go ahead and do it. I'll give you, hopefully a minute's long enough. I'll give you a minute, and then I want you to count up how many declarative facts are required for this problem. And no, typing the numbers in a calculator doesn't count.
on what strategy they use?
Yeah, that could come into play depending on what they're doing, yeah. It would then dictate. And actually, that's something we could talk about in half a second. That was a good point. All right, I'm just going to put it up. Is everyone okay with that? Here's what I counted. Sorry. I counted 16 facts that would be used in order to actually do this problem. And so I have the steps listed out here, but if you're going to find equivalent denominators, you would do 3 times 7 to figure out 21. But then you have to do 21 plus 6. Anyway, so I have them all listed out here. And inherently then, to build procedural knowledge, it's inherently embedded within our declarative facts. And this is where, depending on the strategy you use, if I'm using a very labor-intensive strategy, right? So a student doesn't know what 4 times 3 is. How are they gonna figure that out? Anyone? What might one student do? Yeah, they're going to resort to repeated addition. Well, now, instead of just pulling 4 times 3 is 12, I'm doing 4 plus 4 plus 4, which is adding more facts for me to actually do. Or we can even get into I might have to actually count out, like draw a little picture and go 1, 2, 3, 4. 1, 2, 3, 4. You're adding even more procedural steps to the problem, which is going to inhibit your ability to build procedural fluency in this, this domain. So, I said all that. Conceptual knowledge and procedural knowledge, through a lot of research now, appear to exist together. And I put a lot of text up here, but that's because I'm giving you the slides. I'm not going to read it all. But the Riddle-Johnson paper from 2015 that's cited on the first couple slides for the definitions, that paper summarizes all of this stuff really well. And if you can't get it, I will email it to you. But they've tested this with early numeracy, so things like counting skills. They were working on students going through counting progressions, right? So one-to-one correspondence. And so what they were doing was they were having students build procedural fluency or procedural knowledge in counting, which would look like, here's a set of objects, 1, 2, 3. That's a procedure, right? But then they also were trying to teach kids to recognize errors in other people's counting. So other people would be counting. I'm sure anyone tried to teach kids to count recently. I was doing this with my daughter. I should have put the video of her. But she would be touching an item and being like 1, 2, 3. Right? That's one error students make. Another error students make is they'll touch a bunch of items and only say 1. And so what they were doing was they were trying to say that would show strong conceptual knowledge of the student being able to identify errors in that counting versus just having the procedural knowledge yourself. And basically what they found is both of those seem to coalesce together. Doing both of those types of things was better. There's another article that looked at addition and subtraction and building procedural skills with the concepts of addition and subtraction versus the conceptual knowledge of those. And it once again appeared like both of those things impact one another. Fractions, there's been a bunch of research on fractions because fractions are so dang difficult. And all the time we see conceptual knowledge and procedural knowledge intertwined together as students build. And then lastly, there's been, this last one is for decimal fractions. So we now are seeing pivoting one versus the other is not the way to go. We want to try to tackle both of them together. So how do we do that well? And how many of you are familiar with the CRA framework? Sick. Love to see that. So I just want to go through, there are a couple different ways people refer to this, and I don't want you to be like, oh no, I'm not doing CRA, I'm doing this other one. So concrete representational abstract is the one I see most frequently now, but it had been termed concrete semi-concrete abstract before, which is CSA, and also concrete pictorial abstract. Has anyone ever used Singapore math in here? Excellent. Singapore math, I think, still refers to it as CPA. I'm pretty sure. Has anyone ever heard about how Singapore math came to the US? No? Can I do a quick 2-minute detour? So Singapore was doing amazing in math. A bunch of US people went over, looked at the curriculum, go, sick. They brought it over. Well, the curriculum's like this thing, and there was no instructions for teachers. So they piloted in the US, and it flopped miserably. Teachers were like, what am I supposed to do? And so then they revised it and provided a lot of support to teachers on what to actually do, and now it's actually much better. But it's interesting to see just the difference in teacher training and at the time when they were trying to bring it over. So there's my quick soapbox. So if you walk away with just this today, you're going to be 99 times better if you're not already doing this. This is the biggest, and I'll tell you a funny story. One of the first papers I ever wrote as a doc student, I wrote an article that was explaining this, and it went through peer review and got trashed. And then I called Sarah Powell, really upset. I didn't have, my advisor didn't do math. And I was like, I don't understand. She goes, you're reading bad research. And so Sarah's like, you need to read some more stuff that fits this model. And so then I did. And so here's the difference between these two. In the sequence approach, this is kind of how it began getting tested initially, right? And the reason I like to point people to the CRA is manipulatives are one of the few things special ed and gen ed math people actually are kind of in kumbaya land together. We actually agree that manipulatives and pictorial models are useful. And so it's all about how we use them. So in the sequence approach, what would happen is kids would only use manipulatives, right? The teacher's only using manipulatives, the kids are only doing manipulatives. And then once the teacher's like, okay, these kids kind of mastered the manipulative thing, they then moved to pictures, right? And then the teacher would be doing pictures, the kids would be doing pictures. Once they mastered the picture models, they would then go to abstract. Teachers doing abstract. And that's how the sequence worked. What do you think happened a lot of times in that chained task?
I would think that when I've seen that done with the sequence, that people become very reliant on the manipulatives, and it's hard for them to transition to it being in the abstract. They don't know why what they're doing physically is related to what they're doing on paper.
Amazing. So the response, this is for the video, that's why I'm repeating you. The response was students might over-rely on one of the stages or get stuck transitioning between stages. And that's exactly what they found happen. Kid would be using manipulatives, you'd go to a pictorial model, and the kids would get stuck. How do I do that? And then never mind, to me, that transition wasn't usually as bad. It was, okay, now here's a bunch of Greek letters, what am I supposed to do? And that transition never was happening. So, and you can does everyone clearly see here? Doing that sequence, you are focusing strictly on concepts first, right? You're like, we're gonna build conceptual knowledge through these manipulatives without even discussing the procedures yet. And so in the framework approach, it's different. Instead of looking at these as stages to move through, I'm using all of these things together at the same time. And so, and the biggest difference for teacher behavior, so if you're just thinking about your own behavior, and this is what I tell my undergrads, I need to see you doing the abstract the entire time. That's the biggest change, right? Even if if I'm starting like day one, is everyone with me? Day one, introducing a new concept, I might not be overly focused on the kids doing the abstract yet. But your behavior is, here's the manipulatives, here's how it ties to this thing we're gonna do later. Here's the manipulatives, here's how, and you're making that explicit connection for them from the beginning. And clearly, kids begin engaging in the abstract a lot earlier in that learning process than in the sequence approach. Is everyone cool with that difference there? The reason this is so important, especially for those of you in special education positions or working as interventionists, is the efficiency's sake. So the CRA is not bad. The sequence, sorry. It's not bad. Kids are going to learn. So Stephanie Morano, who actually went to Penn State, so those of you from Pennsylvania, woo woo, right? Stephanie's amazing. And she's now at Virginia, but they did a really cool study, and we honestly need more research like this, and I'll talk about this in a second. But what they did is they compared sequence, so they had kids go through the sequence approach to the framework approach, right? So they basically compared those two. And what they found is both of them worked well. Kids learned fractions, which is great. And the key concepts they were looking at was students estimating fraction magnitude. And this actually might be a decent segue. Those of you, we have a lot of people doing fraction stuff in here. Okay, decent amount. One of the best instruments or assessments to use for fractions is you give kids an open number line, 0 to 1, go plot 3/4. And so what they do in the research studies is they measure how far the distance was between where the kid plotted 3/4 and what's correct. And that estimation of magnitude of fractions appears to be a really pivotal understanding point. But they did these fraction tasks. What do you notice? So sequence, it was 14 instructional sessions. Each was roughly 40 minutes. In the framework approach, it was 8 40-minute. So what do you all notice about the difference in numbers? It's a lot different. Is everyone with me? So they learned the same amount, but this group learned it in almost half the amount of instructional time. That's important. Efficiency of learning is an important need, especially in my role now working in special education, constantly looking at, here's grade level standard, pivoting back. This is where the kid's knowledge is currently. And it's like, I need to increase this knowledge to then increase this next knowledge to then increase this. So time is of essence. It's important. And so the more we can think about being efficient in instruction that's still high quality, it's important. So here's a task, right? I'm working on double-digit addition requiring regrouping in the ones place. And so what you would end up looking like, has everyone seen videos of this being modeled before? Because I can't move them around. If you haven't, I can send you some video clips of people modeling this with base 10 blocks. But what typically happens before, right? This is the before thing. Teachers would be doing this, right? 32 plus 28. The abstract would not be written anywhere. The kids are just moving the blocks around. And so they'd say, okay, we're going to add the ones, right? We add our ones. How many ones do we have? 10 ones. Oh no, we have 10 ones. I need to regroup. I can exchange those 10 ones for a 10, move it into the 10s. We then count our 10s. We have a solution. But students are doing all this. You then jump to the abstract, and it's totally foreign to them of what's actually happening. And so instead, using the framework approach, we would be doing this. But as I do that, I'm gonna move in front of the camera. Sorry, I was told don't go in front of the camera. But now I'm over here. So when we're adding the ones, what we would say is, okay, we're going to add our ones first. We have 2 ones and 8 ones. When we add our ones, that is this spot in our abstract. We have 2 ones and 8 ones. Does everyone see how you just have to make the connection to what these are representing compared to the problem we're doing? In the regrouping step, you say, oh my gosh, we have 10 ones. We're going to exchange them for a 10. Well, what procedurally is that showing? It's when you put the 0 here and you put the 1 up here. And you're helping make that connection. And so the thing, I always use this example because it's the cleanest. It is not always this clean in math. I know that. It's not that clean. But there are a lot of ways we can try to make those connections based on the model we're using, the representation or manipulative, back to this, the abstract. I'll give you a different example. I didn't include this on a slide. Do any of you teach like slope-intercept form? Excellent. We have some people working with older kids. So y equals mx plus b. I was in schools in Louisiana. They were in middle school dying, just dying with slope-intercept form. And I was showing them there's this virtual manipulative app that I can show you. But they were trying to get the kids to conceptually understand when we change b, what is that happening to the graph? Have any of you focused on that? We're changing the y-intercept. And on this manipulative app, what you can do is you could just change the b value and the graph moves with it. It's showing the kids, oh, when I increase that b value, it slides up the scale. When I decrease it, and that manipulative is not bounded by a concrete one. And so I'm going to talk about virtual manipulatives in a second. There's some ways virtual manipulatives can help highlight or show certain math concepts that are really hard to do concretely. All right. This is another lesson I observed one of my teachers doing out in the field, and then we had to have a little debrief about it, and then they went and did it again. But, we're going to work on 4 plus 3. So we're going to count our first set. 1, 2, 3, 4. Let's count our second set. 1, 2, 3. We're going to join them together, 1, 2, 3, 4, 5, 6, 7. We just did all that math. Lots of great models of addition there. What's the problem with this picture? Yeah, is 4 plus 3 anywhere visible up there on the board for the kid? Are we making connections to those symbols, to these the manipulatives? No, right? And so just adding that in and referencing this set of 4 is that number, this set of 3 is that number. This addition means we're joining them into a total, and we're going to count the total set. Oops, sorry, there we go. So within the concrete representational abstract, we have to consider manipulative selection. And within manipulative selection, it's a lot more complicated than one might think. And so there was a really large research study where they looked at all the manipulative studies that have been done. And basically what they found was when teachers helped show kids how to use the manipulatives, it was a lot better than just dumping manipulatives on kids and having them figure it out themselves. So if you're going to use a pictorial model or manipulatives, kind of showing students how to use that manipulative because obviously you're trying to connect that manipulative to the abstract and they might need that support. So showing them how to engage with it and then mapping it is going to be better. The other thing, and this is not from this study, but I can tell you from my own practical experience, trying to do too many manipulative models at one time is also might be detrimental. So if you're doing fractions, for example, we can have an area model, a set model, and a length model. I might not do all 3 of those at one time to highlight a specific skill because it's overload. And so you might want to do one first, kind of transition to the next, and then you might interleave them. But don't go overboard with them. The other thing, which this rarely happens, in those studies, teachers had larger effects than the researchers. So when teachers were doing the intervention, in those studies, the effect sizes were larger than when researchers were doing it, which to me, and I'll show you something else in a second, it shows teachers have very, very, very well likelihood of being able to use manipulatives effectively, which I'm sure a lot of you do. This last one was super surprising to me. Perceptually rich manipulatives were less effective. Now, what does that mean? The manipulative representing something else other than the abstract hurt kids' performance. And so I'll give you an example. I was teaching 5th grade. One of the kids in my class loved Minions. Any of you have kids who love Minions, the movie Minions? So, and he would perseverate a little bit on the Minions. So I was like, oh, I'm going to use these manipulatives that had Minions on it, right? I thought I was killing it, obviously. First year, doing a good job. What do you think happened when I started trying to use those manipulatives to show the math concept? Yeah, he focused on the Minions, right? And so this goes right back down to cognitive load theory, right? Cutting out extra stimuli that's not relevant is going to be better because the whole goal of the manipulative is to help represent that abstract concept we're tying it to. So if the manipulative then becomes, there's a feature of the manipulative the kid's focused on, it might impede their ability to connect it back to that abstract. So blander the better usually for manipulatives. And then this is just ordered by different math concepts, but manipulatives were most effective with fractions. And I keep coming back to fractions because that is a major pivot point in kids' mathematical development, right? We see a lot of students, they might struggle with whole number concepts, but we get a whole new batch of students who begin to demonstrate pretty significant, persistent math difficulties once fractions begin to get introduced. But we can see place value concepts. That doesn't surprise any of us. That connects right to our base 10 system. That's why we have base 10 blocks, and so on. We replicated this actually, but in our study, we only included students with disabilities or at risk for a disability because I was like, I wonder if it's going to be the same for this population. And almost everything was the same in that prior study. The only difference was this age effect. So in the Carbonose study, some of you teach older kids, right? In the Carbonose study, they were like, hey, as kids get older, concrete manipulatives become less effective based on Piaget and all this stuff. In our study, we actually found there was no difference there. So has anyone ever seen algebra tiles? Yeah, algebra tiles, amazing, right? And so I would caution against thinking manipulatives become less effective. as kids get older. Particularly, I know myself, using some virtual manipulatives for different statistical concepts, I find uber helpful to understand what the heck is happening. And I think there were some issues with the other studies saying older kids were less effective. This was one big finding that I'd like to cycle back to. So in our study, kids identified with emotional and behavior disorder, or OHI. Most of the kids in our sample identified with OHI had attention deficit hyperactivity disorder. We just saw way lower effects. And I think once again, and we've seen this in a couple other studies, you can provide the most high quality math intervention known to man. If you are not capturing on good, also dealing with behavior, it's going to be less effective. And so Sarah Powell did a really, any of you know Sarah doing word problem stuff? I have some of her resources I'll share with you as well. They found this same finding in one of their word problem solving interventions. Kids who had elevated levels of off-task behavior responded way less favorably than kids who were on task. And so finding ways to really capitalize on good reinforcing learning behaviors, right, is going to be effective. And so you have to think about embedding some of those components to your instruction as well. Okay, next. So we talked about the CRA. Everyone feels comfortable now, CRA? Framework, not sequence. The next thing we can do is worked examples. And I don't usually do this for things that cost money, but this book is awesome. And it's written by an actual math teacher, a high school math teacher. And it's really cheap, but he walks through how he sets up students studying worked examples within his own classroom. And he has a bunch of examples on there. And actually, I think in my dumpster file, there's also a link to a website that has just a bunch of worked examples for different math concepts. And so what is a worked example? All a worked example is a math problem broken down into steps, and students are asked to study it or evaluate it. So does everyone see this worked example here? This was step 1. What is red was done at step 1. Here's step 2. What's done in red was done at step 2. And so the key part, and this is what that book mentions, is you would have to generate the expectations for how you want that done in your class. So how many of you have ever tried to do a turn and talk? Okay, turn and talk. Quick story, turn and talk. My first year teaching, I was not the best first year teacher. I tried my best though, I promise. Tried to do turn and talks. The kids would turn next to each other, wouldn't say a damn word, right? Or they would turn and just start talking about football. Or I had a lot of kids who really liked to share their opinion, so they would just kind of word vomit on the one kid, the other kid would word vomit back, and then it'd be like, what did they say? And they're like, I don't know. And so me and my co-teacher actually sat and modeled turn and talks, like a whole bunch, after we realized they were going really poorly and wasting time. And so same thing here, explicitly kind of modeling what does it mean to study a worked example. Because if you just one day entered into class and say, hey, study this problem, the kids are just going to look at it and not do anything, right? And so you need to kind of walk them through what is expected. But here's what you embed within the worked example typically. So when you're doing the worked example, students are evaluating, analyzing the worked example, and typically you then have scaffolded questions students think about, maybe talking to a peer or whole class discussion, or they might even write it down depending on how you structure the response formats. But we just studied this. Why is 8 below the 6? Why is this 8 below the 6? Anyone? It's in the ones place. So students are going to talk about that. Does everyone agree that that would be a form of conceptual knowledge you're trying to get students to evaluate? Right? In step 1, why is there a 4 below the 8? Yeah, because 8 plus 6 is 14, and 4 is in the ones place. Does everyone see? That is targeting conceptual knowledge, but also procedures. It's tied into how we're actually doing the procedure for this algorithm. In step 2, why is there a 5 below the 2? What'd you say? There's 5 tens. Where did this magical 10 come from? Is everyone with me? Like, you would just build in these scaffolded questions, which is clearly, does everyone agree here? This is clearly pivoting conceptual knowledge, right? What do they understand about the procedure? But also procedural knowledge. They have to understand how to do the procedure in order to answer any of these. Oh yeah. So, I'm sorry. Let me go back a second. I kept pressing the wrong button. Okay. Sorry. Lost. Dang it. Okay, back. So when doing worked examples, you want to start with correct worked examples. Okay? They're trying to initially learn a concept, and actually, this session I don't talk about this. But if you could read anything on like the instructional hierarchy, which Jared, you and Charles? Okay, they're doing a session on this at some point. But this would be acquisition, right? We're trying to acquire new information, so it's going to be a little bit more, there's going to be more supports put in place. This is useless for fluency building, right? If kids know the procedure, I'm not going to be spending as much time doing a lot of this type of work. So this is good for acquisition. But when we're thinking about building conceptual knowledge as well, right? Like deep conceptual knowledge, what do you notice about these two worked examples? They're incorrect. So what we can then begin to do so don't start with these. Actually, through research, it's been found like there's a whole thing about evaluating errors. I would not recommend starting with errors. It's a useful practice. I wouldn't start there. But then having students pivot on the errors of what is wrong about these? Well, look at Frank's work. Did Frank perform the steps correctly? So here's Frank. No. What error did Frank make? How did it impact the sum? You're building on them really clearly communicating their conceptual knowledge of what was incorrect about this. You could have them correct the solution as well. Look at Wendy's work. Did Wendy perform the steps correctly? What error did Wendy make? How did it impact the sum? And so we're building on both we need to know the procedure to answer any of these, but also conceptually, why is this incorrect? What about the procedure was performed incorrectly? Which is pivoting off of understanding our based end system here. Okay, so any questions on worked examples? Everyone's okay with this? So I have one comment about worked examples. When you start wanting to create worked examples in your own practice, be very careful structuring them. So the old adage, less is better, is going to be very true with this. If you start embedding a lot of extra words that aren't needed, extra things, the student's attention will focus on aspects that might not be critical to the actual concept you're teaching. And the other thing is really stressing. What was I going to say? Nah, it just went out of my head. Okay, less is better. Focusing on the core concepts. Yeah.
Are you familiar with the resource from the SURF Institute, that math by example and algebra by example, and how they'll have like the green one that's like this student's work is correct, analyze that, but then this one is incorrect and they tell them it's incorrect, but they ask these kind of questions.
Yeah, I think that's what I have a link to.
It's free.
Yeah, I'm pretty sure that's what I have a link to in the dumpster file. Yeah, and I think that's really great. Using errors is really beneficial, and this is where one of the most helpful things, as you teach a concept for a number of years, you kind of see what errors are most likely to happen, which helps your practice. And so I think some of the conversation around errors, some people believe allowing students to make errors and then them self-correct their own errors is very useful. The other option is to just prevent the errors from the beginning by clearly explaining this is a pitfall, this is incorrect. And so that's some of the conversation about how to use errors well. I think using errors is a really beneficial practice. I don't think it's inherently needed a student makes the error themselves to then make it useful. So yeah. Okay. All right, so the last thing I'm going to talk about today is self-explanations. And so what self-explanation is it's students generating explanations for themselves in an attempt to make sense of relatively new information. So this is kind of pivoting off. Have you all heard people talking about you being able to teach someone else the concepts, blah, 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 and they have that little pyramid system, and they say lecture is terrible, but being able to explain something is generating your own knowledge. And so this idea is known as self-explanations. And actually, I really cited a lot of Riddle Johnson. So Riddle Johnson did a whole paper on self-explanations. And through their look at the research, there was a couple pivotal things to really consider when having students engage in self-explanation. The first one was, in some of the studies, they didn't teach kids how to do self-explanations. They kind of just said, go ahead and do it. And how do you think that went? Not well. So some of the studies in their sample were college-age kids who are older. Most of you are working with not college-age students. So, and especially if you're working with younger students, really walking through what it looks like to engage in self-explanation is going to be important. So, describing and motivating self-explanation steps, like getting students to buy in that this is important. And this is going to help them learn. Have any of you done cover, copy, compare before? Oh, sweet. Cover, copy, compare. This is a good kind of pivot point. So when you all do cover, copy, compare, do you have students write the answer down? Do everyone? I see heads nodding. So in a lot of, is everyone familiar with cover, copy, compare, how it works? Yeah, I can explain. So in cover, copy, compare is oftentimes used for pretty declarative type fact learning, not necessarily always chain procedures in math. So what you would do is it will say 4 plus 5, let's say. The student looks at it. They then cover it. They then write 4 plus 5 equals 9. They then compare. So as you can see, there's a prompt given. They have a worked example. It's a worked example just for a declarative fact. They look at it, they cover it, they write it, and then they get feedback by comparing. That's the basic cover, copy, compare setup. And there's a couple people at Oklahoma State who have done a lot of work on cover, copy, compare, and it's interesting. Most research does written cover, copy, compare. And a lot of the cover, copy, compare stuff actually came out of spelling initially before moving over to math. And so most of the time it's always written. But in a couple studies, what they found is if you only have 5 minutes to focus on this and you do verbal cover, copy, compare, what do you think happens when you do verbal versus written? Kids get through more. Why? Because writing's slow. And furthermore, they've also tested cognitive cover, copy, compare. And what cognitive cover, copy, compare is the kid just says it in their head. Now, this is the point I was trying to make. What Brian will do in a lot of his research is once he's comfortable, the kid knows how to do cover, copy, compare, he goes, hey, Charles, do you want to do written or verbal today? And Charles is like, verbal, I don't want to write. What is that kid likely going to do in that practice session? They're going to be more motivated. You gave them a little bit of forced choice. They don't have to write. That's cool. And they engage in it very happily. Same thing with cognitive cover, copy, compare. But the problem with some of those is when we begin to switch to something like cognitive cover, copy, compare, I have no idea if the kid's engaging in the behavior or not. So, okay, yeah, they sat there for 5 minutes. Did they do it? I don't know. I don't have a permanent product like I do in written. That's the same issue you're going to run into with self-explanations, right? Because you are putting a lot of faith, right? Okay, they're doing this. When you're probably not sitting next to each of your 25 students in your class listening to them. But building that motivation and helping them see it's important is going to be helpful. Then showing them models of what it looks like to engage in self-explanation is going to be important. And then giving practice with feedback on self-explanation. Here's what some of the studies did do, and this is what I'll show you in a second. Giving structure, right? So some of the self-explanation literature is pretty broad. So let me go back a second. So for this problem, let's say, a teacher could just say, hey, explain the steps in your own words. Is everyone with me? Does everyone see that's very open-ended? Super open-ended, just explain it yourself. For some students, that might work great. For other students, there's not nearly enough structure there. And so what you can do instead is actually kind of fill in for structure. So here's one, I generated one very simple example. But here's our procedure. First, I need to add the digits in the blank place value. Second, I need to blank by place value. Third, I need to add the digits in the blank place value. So everyone see their structure here. So I would be modeling. Students would then be expected to fill in these blanks. You could give them a keyword bank for even more structure. Is everyone following me here? So you can embed as much structure as needed for some students. Other students you might be able to cut back and not need as much structure. But you can begin to think about how could I provide some sort of support in making sure the self-explanations are going to be helpful. And this is where if you're working with older kids, you might just give them prompts, right? It doesn't have to be fill in the blank. This is very flexible. But the idea of having students try to explain the process is going to internalize for them how to do what they need to do. Actually, I don't even have this on a slide. I went and saw some teachers when I was in Louisiana who were doing amazing work related to this. And so what they were doing was, oftentimes the teachers would do some stuff and then students would go and work by themselves, but they were like, I want them to talk about what they're doing. So then they would try to do turn-in talks and stuff like that, and it didn't go anywhere. They kind of flopped, And so they were really struggling with what could we do to help them begin to verbalize their steps and get feedback from someone. And what they did is they paired students up. One person was the talker, the other was the scribe. Is everyone following me here? And then they would flip-flop roles. So the talker would say, this problem would be presented with nothing done. And the talker would say, first we need to add the digits in the ones place value. The scribe would do it. And the scribe was tasked with doing exactly what was said. Because then at the end of the cycle, you now have a completed work example both of them could evaluate together. Then they flip-flop roles. And so as you can see, if you pair students well, you have a good feedback step there. You're getting practice with verbalization. Someone's giving them feedback on, that doesn't make sense, right? And depending on how you structure it, this is what I would do. Whatever task it is, you could say something like, these words need to be used, right? So if you're trying to really target vocabulary, say, these 4 words, whatever we're doing, they need to be used in your self-explanation to begin to get fluency in not only hearing, but using the vocabulary accurately. Okay, so any questions on engaging in self-explanation right now? We're good here? How much time do I have left? Okay, I'm probably going to end early then. Sweet. All right, so last, with thinking through conceptual and procedural knowledge, is how to use appropriate practice. And so I'm sure that this is probably review for a lot of you, but we have different types of practice we can engage in. We have something that we might refer to as blocked practice, and then we have something we might refer to as interleaving practice. And so in blocked practice, how that's structured is, let's say I have 2 skills that were kind of taught. Is everyone okay with that? 2 skills. I'm going to call them A and B. I would say, okay, we're going to do some practice, and I'd be like, problem 1 is skill A. Problem 2 is skill A. Problem 3 is skill A. Then we'll transition to skill B, skill B, skill B. Does everyone see how they're blocked together? That is great for initial acquisition. Why is it great for initial acquisition? Because they're getting repeated practice of the same procedure without having to overly think about different competing interests. However, it eventually becomes beneficial to switch to interleaving practice. What does everyone notice about the interleaving practice there? Yeah, they're mixed together. And this is where I would, and actually, no, I did do this because I was thinking about it. You wouldn't want to just go A, B, A, B, A, B, A, B, because then the students are very smart. They're going to be like, oh, they're just alternating. So you would just make kind of a random list, but they're going back and forth. And this is really great, which Jared and Charles will talk about. The idea of being able to discriminate which procedure to use. Is everyone cool with that? Discrimination. That's literally what this is, okay, here's a problem. I need to look at it, analyze it. Which procedure do I need to use for this specific problem? And by interleaving them, you're forcing students to engage in that thought process when doing it. And I think I have an example. Yeah, this is from a math curriculum. And you can see 1, 2, 3, 4, 5, 6, 7, 8, 9. What do you notice about how they set up the practice here? Yeah, great. Does everyone see it's blocked here? And so the first 3 items are all the same skill. Multiplying fractions that are positive. The second 3. Oh, no, actually, no. Only the second 2. 1 negative, 1 positive. 6. So there's only 1 for that one, and then the last. Is everyone okay with this idea, though? And so this is blocked, and this is the thing. It's not either or, right? It's not like I'm only doing blocked, I'm only doing interleaving. It's like when to use which one. And so blocked initial, building initial conceptual procedural knowledge of it, and then when you interleave, it deepens that conceptual knowledge of when should I be using this. This is just a pet peeve of mine, so I'm going to share it. I love word problems, and I wanted to talk about word problems, but I think there was already another session. A lot of people will do this. Students will now solve problem number 10. Is that problem solving? Yeah, because we literally just spent, so here's how I typically see it structured. The sheet will be like addition, 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 word problem. What do you think that word problem is? Addition. You're basically testing if they can pull out the numbers and do addition. So that's not how to teach word problem solving. But that's just my pet peeve. So, oh no, now I feel very self-conscious. So I have two word lists listed here. And so we have scenario 1 and scenario 2. If you will take a look at those really quick, top, bottom, which list is organized by block practice? Wait, which one is blocked? No, the first one's blocked. Yeah, the first one. So in the first list, we have CVC, 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 and then we switch to CVCE, CVCE, CVCE. So that first one's blocked. The second one is attempting to be interleaved. Does everyone see it's not all the same order? And so this is where you might use one versus the other depending on where a kid's initial knowledge is. We don't have to talk about that. Okay, so here's my last, I think this is the last slide. So within math, right, we need to really think carefully about doing this. So I have a basic chain here of something you would be teaching in, I think, roughly 2nd grade usually. So we have 2-digit by 2-digit addition without regrouping. Okay? We've all taught that if we teach those, if you've worked with younger kids. You'll then likely transition to 2-digit by 2-digit addition with regrouping in the ones place value. You then likely will move to 2-digit by 2-digit addition with regrouping in the tens place value. And then you'll probably move to 2-digit by 2-digit addition with regrouping in the ones and tens place value. And I have sample problems here. And this seems like overkill, but when I look at a lot of curriculums, they don't do this for you. It literally is no regrouping, regrouping, and they don't disentangle the complexity of what's being asked. And so thinking through that is critical so you're not bombarding them with, oh my gosh, regrouping in all these different place values. And so let's say we're like at this stage, right? So I'm teaching this as a new skill. So now students are working on regrouping in the tens place value. If I have a math intervention or even just math instructional time point, I'm going to probably be using blocked practice for that skill. Is everyone cool with that? There's going to be a bunch of problems for that skill. In that same math session, though, I can do interleaving. What would I interleave? The previous 2 skills. And so I like to share this because your curriculum probably doesn't do this well. And so this would be something that you would have to think through of like, what do I want blocked? What would I want to interleave? Because relying on your math curriculum you're given might not do that overly well. And so you might have to kind of massage things a little bit in order to get it that way. The only thing some kids do, which this drives me up a wall, a lot of my undergrads are administering CBMs out in the school, and they're running into this issue. They're doing like multiplication problems, and the kid just skips around the page to do the ones they know, and then they go back and do the next ones. Oh, where are all the zeros? I'm going to do all those first. And so that can screw you a little bit when you're trying to purposely interleave. I would say, though, if the kid's able to, let's say you were doing this and the kid goes and solves all these first, they show conceptual knowledge. Why? Why would that be them showing conceptual knowledge if they went and found all those? Yeah, in order to identify them, they had to know they didn't require regrouping. So it's not the end of the world. It really isn't. Because they're showing knowledge by doing that. Okay, so here's my last point. And I will take you to the dumpster file thing just to show it to you. This QR code will route you there. If you can't get the QR code, that bit.ly at the bottom. And then that is an open folder, so just save the link and you'll always be able to go back to it. Okay, if the QR is not working, I promise you can come scan my computer, but I'm going to go to the link really quick to show you one thing. All right, this is the trash folder I kept telling you about. So there's a lot of stuff in here, but if I could point you to like one really good place to start. Why is my computer not scrolling? Did I miss it? Oh yeah, this one. So if there's a place I'd recommend, like if you have time, I would go here to just look for a second. And so a couple people who do a lot of math intervention type stuff put together this 8-course module. It's all online, it's all free, and it walks through literally the entire database individualization framework, which the National Center on Intensive Intervention walks through. So it walks through all those parts of what it would look like to set up intervention for math at your school site. But within it, the middle couple modules cover specific math concepts you might be introducing a lot. So it covers whole number operations. There's a whole module on fraction whole number concepts, and fraction concepts. And in the video, something I wasn't able to cover all the math content everywhere to show what conceptual and procedural knowledge might look like. That's what this will do. So it'd be like, I'm teaching this fraction thing. What would be like the conceptual knowledge building I would be doing and procedural knowledge building, and what might that look like? And so that's a really good starting place for some of this stuff. And if any of you are at elementary grade, this is an entire free math intervention program focused on additive word problem solving. What's nice about it is very focused on additive word problems, but with the way the program works is they focus on number concepts as well, so building fact fluency in addition. They also have pre-algebraic reasoning within there, so you think about the equal sign. 10 is the same as blank plus 4. That's embedded within each practice session, along with computation. And so it's almost like they threw everything that's really important into this one intervention program, so it's all within there. But, okay, I am done. If you have questions for me, I will stay up here. If you need my email again, I can give you that as well. If you want to scan the QR code, I'll put it back up on my laptop. But thank you all for coming.